oldest sciences practiced by mankind. Much of astronomy is looking through a telescope at objects in the night sky to observe, collect data, and understand outer space, such as the moon, planets, comets, and stars. Today, in addition to optical telescopes, astronomers use radio telescopes to collect information about outer space that cannot be seen. Radio telescopes are radio antennae that look into outer space by detecting and collecting data of electromagnetic radio frequencies that we are not able to sense with our eyes. Almost all astronomical objects emit some sort of radiation as radio waves, and radio telescopes allow us to image objects such as galaxies, nebula, and pulsars. A radio telescope collects information about the radio emissions of objects in outer space. This data is often sent along the internet to banks of computers to be processed, analyzed, and output as images of astronomical significance. Astronomers are trying to understand outer space through the widespread use of observation and mathematical models to answer many questions. What is the universe made of? Why does the universe have the structure we see today? How did the universe evolve? To help answer some of these questions, astronomers can send their complex data or numerical models to the world's largest distributed network of computers called the TeraGrid. Spread across multiple sites around the United States and linked by a high-speed internet connection, the TeraGrid allows large numbers of computers to work together to analyze and make sense of immense amounts of information. The TeraGrid is capable of linking together multiple computers to make over 250 trillion calculations per second. That's more calculations than 80,000 desktop computers. The TeraGrid is also capable of storing over 30 petabytes of information as digital data. That almost equals all of the written works in the history of humanity, or 6.3 million DVDs. Why would astronomers use the TeraGrid?
Well, the TeraGrid gives astronomers a new tool for discovery, from optical telescopes that see light, to radio telescopes that listen to very minute signals, to X-ray telescopes that look at very hot objects in the universe, to even theoretical numerical simulations. All of this data is enhanced by the immense computing power of the TeraGrid.
This simulation, which took weeks to compute, is a model of the formation of galaxy clusters in the early universe and shows the effects of black holes. Black holes heat the surrounding gas, changing rates at which galaxies form. This simulation shows a section of the universe over 107 million light years across soon after the Big Bang, and the simulation lasts for 1.5 billion years. This is a simulation of a region of the universe that's about 20 million light years across, as seen at about 2 billion years after the Big Bang. We're looking at a volume rendering of diffuse gas density that traces where galaxies are located. This is a comparable volume, looking at the buildup of a galaxy cluster from very early in the universe to the present day, roughly 10 billion years. The TeraGrid allows astronomers to run very complex simulations comparable to the size of the universe. These simulations allow us to model galaxy formation, the influence of black holes, and the structure of matter in the universe. People have been looking at the stars from the beginning of humanity, and now we have the tools that allow us to experience more fascinating and awe-inspiring things than ancient people ever imagined. These tools help us answer the questions: how did we get here? And where are we going?